Hey guys, welcome back to week 4 of my series where I'm learning ML through an optimization perspective. So this week I'm in the Boyd book, so I covered sections 2.4 on generalized inequalities and 2.5 on separating and supporting hyperplanes. I also reviewed material from the previous week, so in total I spent about 9 hours studying this week. Lastly, sorry about the late upload. I've been super busy with work and real life stuff. So this week was pretty cool. It involved a lot of thinking about math in general and connecting previous concepts from chapter 2 with the new material. So the main things I learned were the generalized inequalities and separating hyperplanes, which I'll show you more in a bit. I thought the generalized inequalities were really cool because I get to see how we can naturally generalize something so familiar to me, which is regular inequalities. I also talk about an application and statistic using positive semi-definite matrices. So this week, because I was super busy with work and real life stuff, I couldn't get around to doing many practice problems. So next week, my plan is to cover the final 2.6 section and then work through a bunch of problems to review the entire chapter. I might even design a test for myself or something like that. But this might involve a couple of weeks or so before I move on to chapter 3. So to understand generalized inequalities, we should first understand regular inequalities in such a way such that the generalization is natural. Consider the inequality y is greater than x. What does that really mean? Well, your intuition is telling you that it's obvious what it means. It means that y is bigger than x, or even that y is on the right side of x on the number line. But how can we understand bigger or right side in a more rigorous way? So here's how to do it. So first notice that y greater than x is obviously the same as y minus x is greater than 0. So the interpretation is that the difference must be a positive real number. In fact, we can say that y minus x is a set of positive real numbers, which we call r plus. So if we draw the number line, then y minus x must belong to this set, the positive half. So looking at the last expression, this also begs the question, why not allow other sets besides the positive reals? What about, for instance, the positive orthant? If the dimension is 2, this would look like an extended number line in the orthogonal direction. What about some other set, let's say K? So what properties of the set K do we need to define valid generalized inequalities? Well, we want to generalize inequalities, so we must think about what properties of inequalities must remain true. In particular, if theta is positive, as you can see here, then y is greater than x implies that theta y is greater than theta x. Or equivalently, if you move the right side to the left side, we can see that theta, parentheses, y minus x, still belongs to the set. Therefore, our set K must have the property such that if x is in the set, then some positive multiple of that value or vector must also be in that set for positive scalars. But recall that a cone is exactly this definition. Thus, our set K must also be a cone. We would also like K to be convex. Remember, that just means that if x and y are in K, then any point in the line segment between them also is in K. So this should make sense. If x and y are both positive, then any weighted average between them, like x plus y over 2, is also positive. Combined with being a cone, this gives us the property of transitivity. In other words, if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. Using the properties of cones and convexity, on screen is an argument for why that is true. We would also like K to be closed, meaning it contains all its limit points. So this is a concept from real analysis, so I won't go too deep into it, but basically the boundary of K is also included in K itself. We would also like K to be solid. This means K has a non-empty interior and is full dimensional. So consider the images on screen. In R2, or the XY plane, the left side is full dimensional because it contains values in all of the dimensions. However, on the other side, the value is only constrained to a single dimension. So we see that the second one is lower dimensional and not has a full interior. Finally, we would like K to be pointed or not contain any lines. Consider the number line again. Notice that the positive reals don't extend to the negatives. This means it's not a line. This means if that x is in K and negative x is also in K, then x must be 0. So this is important because if x is less than or equal to y and y is less than or equal to x, then x minus y is in K and y minus x is also in K. So by this pointed property, this means that x minus y equals 0, which of course implies that y equals x. So if we didn't have this pointed property, we could not conclude that x equals y given these two properties of x and y. Now let's look at some examples. Consider when K is a set of all positive vectors. So this is just the positive orthants. So this is the same positive orthant I mentioned earlier. So for n equals 2, we recover the familiar positive xy orthant. We can verify that this set is a cone, convex, closed, solid, and pointed. Now let's consider what is meant by the generalized inequality x is less than or equal to y under this cone. Well, what this means is that y minus x is also in the positive orthant. So for a vector to be in the positive orthant, each entry must be non-negative. Therefore, for each y, yi minus xi, so just the components of y and x, must be greater than or equal to 0 for all y and x. So the generalized inequality over the positive orthants simply means component-wise inequality. So each entry of y is greater than or equal to the corresponding entry of x. So now maybe a more interesting example is let's consider the set of positive semi-definite matrices. So we represent this set of all positive semi-definite matrices of dimension n as simply just S of n positive because it's semi-positive. So we can verify that the set is a cone, convex, closed, solid, and pointed. So take for instance two matrices x and y in this set. So if x is less than or equal to y under this set, then y minus x also must belong into the positive semi-definite set. This also means that for any vector z of appropriate size, we have z transpose x times z is less than or equal to z transpose y times z for any z of R of n. So there are many applications of this idea, so let's look at an example from statistics. So let x be a random vector with covariance matrix sigma. Then for some vector z, which is the same size as x, we can show that the variance of z transpose x is equal to z transpose times sigma times z. So this variance equation should look familiar, and so we're going to use that description with semi-definite matrices. Recall that an ellipse, or More precisely, an ellipsoid is given by the following equation. Now let's draw some pictures. If the components of X are uncorrelated with an equal variance, meaning that sigma is the identity matrix, then our ellipsoid is a sphere. So here we can say that X has only two components, so it's two-dimensional, and we can see that X1 and X2, so the components are uncorrelated. And what that means is that if we sample X many times with this distribution, then a single sample might look like a single dot on this graph. But if we sample many times, we will see that we get a circle shaped because their X1 and X2 are uncorrelated. On the other hand, if the components of X are correlated, we get our familiar ellipse. So in this case, X2 and X1 are positively correlated. That's why the ellipse is oriented the way it is. So let's think about geometrically, what does variance of Z transpose X really mean with these ellipsoids in mind? So first we have to draw some vector Z in some direction. So we project each sample onto this direction. Then we ask, after sampling many times, what is the variance of these projections for any given Z? Notice that if X1 and X2 are positively correlated like we had before, and Z is aligned with the major axes, or here, then the variance will be larger. This is because when we project onto the Z line, we're more likely to be farther along the Z line because the ellipse is sort of shaped like this. On the other hand, if Z is perpendicular to the major axis, the variance will be smaller with the same argument, but just in reverse. So that completes the setup. So now we ask, for two datasets A and B, what does the generalized inequality sigma A is less than or equal to sigma B? Well, it turns out this means two things. One is dataset A has a low variance along any projection Z. And that means that the ellipsoid of A is a subset of the ellipsoid of B. In other words, A is less spread out than B along any axis. So I just like to walk you through why that's true and how we can argue that mathematically. Well, to show something like this, we always have to start with what we're given. And we're given that sigma A is less than or equal to sigma B. And so this means that the difference is in the set of semi-positive definite matrices. And since the difference belongs to a set of these types of matrices, we know that for any Z, we have Z transpose difference times Z is greater than or equal to 0. So we can arrange this term as follows. So notice that this equation looks familiar. This resembles this variance equation, right? So we can plug in sort of these values here. So now we've arrived at a result, and we've completed our argument for step 1. We've shown that for any vector Z, the projection along the Z for some sample X, you take the variance of that, and that must be larger for dataset B than compared to dataset A, assuming that sigma A is less than or equal to sigma B. Now for step 2, we want to argue that the ellipsoid of A is a subset of ellipsoid of B. First, note that sigma A is less than or equal to sigma B implies that if you flip the inequality and take the inverse, you have the following result. Okay, so with this in mind, our strategy for showing that the ellipsoid of A is a subset of ellipsoid of B is to simply just take some vector x,
from the ellipse of A and show that it must also belong to the ellipse of B. It immediately follows that since x is in the ellipse of A, that x transpose the inverse of sigma ax is less than or equal to 1, just by the definition of an ellipse. And using the property above, we know that this inequality must be greater than the similar inequality for dataset B. And so now we have a chain of inequalities as follows. But notice the structure here. This is the equation for the ellipse of B. And since that this is also less than or equal to 1, x must be in the ellipse of B as well. So since we've shown that any vector x from ellipsoid A also exists in ellipsoid B, we have shown that ellipsoid A is a subset of ellipsoid B. So I just thought this was really cool and I wanted to show you guys. So now we have a way to compare the variance of datasets using the positive semi-definite cone ordering, and we understand what that comparison actually means geometrically.
So this week again was really cool. The example with positive semi-definite matrices has so many applications. For instance, in civil engineering, buildings must be able to withstand, deformation up to a certain threshold when forces are applied in any direction. So what you would do is you model the building structure with a stiffness matrix. Then you would apply the generalized inequality for positive semi-definite matrices to create a constraint that describes how much the structure can deform under forces from any direction. So there's many applications in control theory, machine learning, and financial portfolio optimization. Basically anywhere you need to reason about variance, covariance, or quadratic forms. So as for next week, I was pretty busy with real life stuff and work this week. So I think next week will be similar actually. I'm pretty busy with work. However, my goal is to finish chapter 2 with the final section 2.6 and work through more practice problems. So I'll see you everyone next week.